Hey y'all, it's your main math teacher, Mr. Boyden. I'm back at it again today, and today we're going to be talking about how to find volumes. Specifically, we're going to start with prisms and cylinders. Volume is very similar to our prior learning with area. Area, we wanted to know how much surface something covered. With volume, it's the same idea, except today we're going to operate in 3 dimensions. So you may remember how in the past, with area, we would say that we ended with centimeters squared as a way of describing our units. Today, it would be centimeters cubed. And the way you can think of that is it's 3-dimensional figure, so its measurements are going to be 3-dimensional measurements. So let's start with this example. We're going to dive right in today. We want to find the volume of the prism. Now, for volume of a prism, what I'd like you to put down in your notes is this: area of base times the height. Now, the reason I write it out like this, oftentimes in books, people write like this. They'll say that. They'll say volume is base times height. The problem is, what a lot of students do is they don't realize that B is an uppercase B, so they don't think of it as an area. They go, oh, the base is 3. That's not correct. I'm going to show you why. Okay, so we say area of the base. First, we're going to look at our prism. Where's the base? It's right down here. Its area would be 3 times 5. So volume, I'm going to have 3 times 5. And then we multiply by the height of the figure, or of the solid. So there you go, 5. And so now we have 3 times 5 times 5. So we get 75 inches cubed. Okay, that's our first example. Now notice a minute ago, I used the term solid instead of shape. This over here is not a shape. A prism is not a shape. Shapes are 2-dimensional. When it's 3-dimensional, we call it a solid because it actually takes up space and it's physically something that's solid. So this is going to be our first solid that we've worked on. Let's do another example. In this example, we have 2 friends, George and Annette, who are living in apartments that are next to each other. In George's apartment, the floor plan is 20 feet by 30 feet. Oftentimes, the size of a building is measured by its floor plan, and we'd say, oh, this house is so many square feet. So his is 20 by 30 feet. With an 8-foot tall ceiling. Annette's apartment is 20 by 27, a little bit smaller than 20 by 30, but the ceiling is 12 feet tall. Who lives in a bigger apartment? Well, a realtor who was marketing it would definitely say that George has a bigger apartment. 20 by 30 is bigger than 20 by 27. However, if you've ever been in a building that has really high ceilings or really small ceilings, you know that ceiling height matters. So let's do a mathematical comparison of these 2 apartments to determine what we think is a larger or a bigger apartment. So the way I'm going to do this is with a table. So let's do an area calculation, and let's do a volume calculation. And we'll do one for George. And we'll do one for Annette. And we'll just organize all of our work right here in these boxes. Okay, so when I do area for George, the area of the floor of his apartment is 20 by 30. And so when we do that, we get 600 square feet. What about Annette? Hers is 20 by 27. So we're going to do 20 times 27. And I get 540 square feet. So this is why a realtor would say, see, George has a big apartment. Very nice, big, spacious apartment. Annette's is a little bit smaller. But let's see how that changes when we deal with volume. Now remember, we had area of base multiplied by the height. Well, we already found the area of the bases. So that's going to be 600 times how tall are the ceilings in George's apartment, though it's 8. And for Annette's calculation, the area of the base, we already figured that out, 540 times the height, and her ceilings are 12. So let's figure out what these are. 600 times 8, that's 4,800. And that is cubic feet, or feet cubed. And 540 times 12, we get 6,480 cubic feet. So this tells a very different story. So now we say, wait a minute, but Annette's apartment is way bigger than George's. It's not even close. If you were in there, you would think, or if you were in the apartment, you would think, well, yeah, look how big Annette's apartment feels. And usually that's what people say, oh, it feels very big. It's not very big, but it feels big. Because people say, well, George's is bigger. So how do we answer this question? Who lives in a bigger apartment? Well, folks, this is one of math's debatable questions. It depends on how you measure it and how you look at it. If you're looking at area, George has a bigger apartment. But if you're looking at volume, Annette has a bigger apartment. So it really is a matter of preference, but it's something to be aware of, as someday many of you are going to be shopping for apartments, houses, office buildings, whatever it is, and you can take these factors into account to potentially, who knows, maybe get a better deal or something like that. Let's do another example now. Okay, here's another example of a prism. Maybe we should talk about what a prism is. A prism is given that we have two ends, okay, and here the ends are triangles, and the two ends have to be the same shape. They can't be different, so here they're triangles. And then they have these faces that connect them, and those faces have to be parallelograms. In our case, at our level, they're typically going to be rectangles. So here we have two ends that are triangles. So remember, what we're going to do is area of the base times the height. So we have area of a triangle in this case, because that's the base, multiplied by the height. Now the height gets a little bit confusing for people, but one way you could think about it is if I slice this up like a loaf of bread, the height is given along the length of the loaf, okay? So 40 is actually the height, or if you tipped this thing up, so this base was sitting on the ground, and then the height was vertical, that would help us understand that the height is 40. So we need to find the area of the triangle, and then we need to multiply that by 40. So let's start finding the area of the triangle. Area of a triangle is base of the triangle, that's 20, times the height of the triangle, which is not 29. 29 is on that hypotenuse. And that's what I need to find. So base times the height divided by 2, and then we said we're going to multiply that by 40. So I'm going to need some side work. In fact, I noticed this is the Pythagorean theorem to find this. So I get 20 squared plus x squared equals 29 squared. Okay, so I get 400 plus x squared equals, what is 29 squared? That's 841. Okay, we're going to do some basic algebra steps now. And so I get x squared equals 441. So that x, and remember we're square rooting now. We've done this 100 times now, I think. Okay, so then we get 21 for that height. Now, so I'm going to go back and label that on the picture. And then that was the height. So I get 21 right there. And now it's calculator time. So we're going to type this in. 20 times 21, divide that by 2, multiply that by 40, and I get 8,400 cubic meters. Okay, so just like we learned in the area section, we sometimes will have to do a little bit of extra work to find some lengths that we need. That's okay. We'll just do the work, we'll plug them in, and off we go. Now let's change gears for just a minute and go to cylinders. Now, cylinders work the exact same way, and because if you don't know a cylinder, think of it like a soup can. Okay, a soup can or a pop can is a really good example of a cylinder. It's like a prism, except the base, instead of being a polygon, the base is a circle. So like cylinder, like a circle. Okay, so circular bases. So it's still the same formula. Volume equals area of the base multiplied by the height of the solid. So for us, for a cylinder, the area of the base, if that's a circle, area of a circle, do you remember that? You might have to look in your notes. That's pi r squared times the height. So this is the official, if you look it up, that's the official formula for the volume of a cylinder. You'll want to make sure to have that in your notes. Now let's try this question. The volume equals pi times the radius. Can you tell what the radius is? Okay, a lot of people say 16. It's not. Here's our circle down here. Okay, our radius is actually 8. So if we have 8 and we have 8, whoops, redo. If we have 8 and 8, that totals 16. So we actually get 8 squared. How tall is our soup can, our cylinder? That's 9. So 8 squared times 9. They asked me to leave it in pi, so I'm going to my calculator, but I'm not typing in pi. I'm just typing in 8 squared times 9, and what I get when I do that is 576 pi. And in this case, feet cubed. Now, one thing I haven't talked about yet that might bother some of you, especially if you're at home trying to take notes, and I'll actually go back to the prism in a second, I apologize for leaving this out, is I didn't talk about how to draw these. Now, those of you who've been watching my videos for any length of time or have been in my class, you know that drawing is not in my skill set. This is not something that I have any talent in whatsoever. However, even I can draw a cylinder, so let me show you the trick. So what I'm going to start with is up at top. And the thing that used to throw me off is I'd start by drawing a circle and wonder why I couldn't get a cylinder off of that. That is not a good way to start drawing a cylinder. Because it's a perspective drawing, we're looking at an angle, we need to draw basically an oval. Okay? From that oval, we can come straight down. And then at the bottom, we're going to finish off our little oval like that. Now, That's not a super neat looking cylinder, but I can tell that's a cylinder. I can label its radius as 8. I can label its height as 9, and I can still get the gist of what's going on. Now, let's go back to prisms for just a second, and I'm going to show you how to draw those. Okay, so how do I draw them? What you often want to do is start with a face. So I'm going to show you how to draw a cube. The way to draw a cube is to start off with a square. Okay, and you can already see my lovely, lovely drawing skills on display. Then we're going to draw some little tails off of these. All of them need to be the same length, and they all need to be parallel to one another. And then all we do is connect them. And boom, there you go. You have a cube. And if you wanted to make this one, you would just draw a rectangle as the face. It would be no different. Okay, it's the exact same idea. Notice on here, each of these, these are parallel and the same length with the way they're drawn. Okay, so that kind of gives us a hint that that's what we would need to do to draw these in our notes. Okay, so let's not necessarily bump up the difficulty, but go a little bit deeper into this concept with something called Cavaliere's Principle. Okay, and you do not need to know this by name, but basically the idea of Cavaliere's Principle is if I take my stack of coins and I skew them a little bit, something like this, or if I just push them to the side, are they taking up the same volume, or did I make them take up more volume or less volume by doing that? So as you can see, we have 12 coins here. It's still the same amount of coins, and each coin is still the same size. I didn't change their size by pushing them to the side. And so what that tells us is we have the same volume. Now, why that matters is if we have a skewed shape. Now, really, this isn't quite a new concept. In the previous lessons, we learned about rectangles, and if you sort of skew your rectangle to make it a parallelogram, we learned that that doesn't change the area because this little triangle just moves over here. Okay, that's all it is, and it fills in this space right there. And so it's still a rectangle. Same idea applies to volume. How are we going to use that? We would use that understanding in an example like this one. Okay, so again, we have a cylinder, so it's going to be pi r squared times the height. So that would be pi r squared. The diameter is 8, the radius is 4, and the height is 12. It's going straight up and down. They demonstrated that with the right angle right here. And so I'm going to leave this one in terms of pi. So what I get is 4 squared times 12. That's 192. So I have 192 pi cubic centimeters. Okay, and that's all. So if you see that the shape has been skewed a little bit or slanted to the side, don't be intimidated by that at all. Cavaliere's Principle tells us it's going to work the exact same way. Sometimes we'll end up with a composite figure, and this more accurately mimics the types of things that actually come up in life where we would actually need to do these for our own reasons or for our own interest. So one thing that's nice about them calling this composite meaning that they put together multiple shapes into one, that indicates to us that we're able to break this down into other shapes. And so the way I'm going to do it on this one is I'm going to put a little cut right here and a little cut right there. And you have to imagine that cut going all the way back. So now I have a box on top, and I have 2 smaller boxes down below. I'm going to call them A, B, and C. The reason I do that is because I'm going to organize my calculations one at a time. I'm taking this challenging composite problem, and I'm going to break it down into 3 easy problems. So I'm going to start off with A, and I can see that A is a box or a prism, and so that's going to be the area of the base, 4 times 6, times the height, or maybe the depth, if you wanted to think about it this way. How far is this going back? Well, they told us up here it's 25, so it's going to be uniform given that this is a prism. So that means my height is 25. So let's find the volume for A, 4 times 6 times 25, and that is 600. Let's go on to B. Area of the face, or of the base. Base, face, you could probably use those interchangeably for prisms. It might be easier for some of you if you think of it as a face. Okay, so I have 14 as the width. The height, I got to be a little bit careful. Okay, I'm going to think about the height right here. Now I know the height of the total solid is 10, and this is 6, so that must be 4. 4 plus 6 gives me 10. So 14 times 4, and the depth is still 25. So 14 times 4 times 25, I get 1,400 when I do that. And let's go to C. Now folks, notice that C and A are the same, so I'm going to spare myself the calculation. I know that's going to be 600. At the end, I'm just going to add those 3 results together to get the total volume. And so what do I get? I get 2,600 cubic centimeters. Okay, so the only note I want to add to this is you'll have to be a little creative. Some people prefer to make their cuts like this, and so they have kind of a tall skinny prism, and then a square looking, I don't think it's technically square, but a square looking prism in the middle. So that works absolutely just as well. You technically, if you wanted to, could make your cuts like this, and then all of your faces would be trapezoids. I don't do it that way because it ends up being extra work when you have all these trapezoids you have to find the areas of. I want this to be as easy as possible. So I don't do it that way, but you totally could. Let's move on now and talk a little bit about pyramids and cones. In order to do that, we need to make sure we have the basic skills necessary to be able to get through these types of questions. And so as you can see here in these diagrams, one of the common themes is we're going to need to know the height. Now on a cone, you can't measure the height out here. Do you know why? Because it's slanted, okay? It's not going straight up and down. Heights are measured perpendicular to the base, or as we would say colloquially, they're measured straight up and down. And this 15 isn't. So we need to be able to find the height. Now on question 1, do you have any ideas on how we could find the height? If you do, or even if you don't, pause the video and see if you can find all these missing lengths on your own. Okay, the way we're going to do this is going to be the Pythagorean theorem. I'm going to get 9 squared plus h squared equals 15 squared. And then when I do that, I get 81 plus h squared equals, I believe it's 225. Let's double check just to be sure. Yep, 225. Okay, we're going to subtract 81 on both sides. And so I get h squared equals 144. And y'all, I'm not showing the step. Show the step if you like it, right? Minus 81, you can. Okay, I'm going to square root that, and I get h equals 12. Okay, now if that made this make a little more sense to you, pause the video again. Now try number 2 and 3 on your own and see how you do them. When you're ready, hit play. Okay, on this one I have to be a little more careful because how long is this side? Okay, some people will jump and say, oh, it's 12. It's not. 12 is this entire length. If it went all the way across, it would be 12. But heights go down into the middle, so that's 6 and 6. So what I have is 6 squared plus h squared equals 10 squared. Hey, a little bit easier numbers this time. So that's 36 plus h squared equals 100. I'm going to subtract 36 on both sides, so I get h squared equals 64. And then I get h equals 8 after I square root both of those. Okay, so 8 on that one. What about the last one? Okay, again, pause the video and try it on your own if you're ready. 1.5 squared plus 2 squared equals L squared. I think I need a calculator on this one. 1.5 squared, that equals 2.25. So 2.25 plus 4 equals L squared, which means 6.25 equals L squared. I need to square root that, so square root of 6.25 gives me, oh cool, 2.5. So I get 2.5 equals L. So square root both of those, right? So if you want to put that in your notes, you can. Okay, now that we have the basic skills, let's try to build the concept based on what we already understand about prisms and cylinders. And so the question is, how do cones relate to cylinders? And how do pyramids relate to prisms? So I've included 4 diagrams here so you can try to make the connection. You see how this cone, and every cone for that matter, fits really nicely inside of a cylinder? So that would tell us that the volume is less than the volume of the cylinder. But the question is, how much of this cylinder is filled up by that cone? So that's kind of a hard question to answer, actually. It's kind of tricky to think about. So I'm just going to let you know. Now, guys, a cylinder, we said that the cylinder was pi r squared times height. It turns out that when you have a shape inside of a cylinder or prism that comes to a point at the height of it, so it comes all the way to the top, fills it up, that what we have, so that's a cylinder, I put CY. For a cone, it's going to be 1/3 of that same volume. So 1/3 pi r squared times the height. Now, for a prism, we had the area of the base. I'm going to put AOB because we've pretty much already established that. So volume of a prism is area of base times the height. Pyramid is going to be the same thing. It's going to be, so I'm going to put volume of a pyramid, PYR, is going to be 1/3 times the area of the base, AOB, times the height. So now that we have those out, let's do a few examples and get good at them. Okay, here's our first example. Okay, this is an arena that's in Memphis, Tennessee. It's called the Pyramid because it's a pyramid. We know that the area of the base is 300,000 and the height is 321. So we said a minute ago the volume of a pyramid is 1/3 the area of the base times the height. So let's fill that in. 1/3 the area of the base. Okay, they said 300,000, 300,000 times the height is 321. Calculator time, y'all. And I get, oh my goodness, quite a big number. Okay, I get 32,100,000. And that is cubic feet. Now you go, whoa, that number's too big. Not really. I mean, you need a lot of space to have an arena. Arenas are really big. You know, you got to play sports in there, maybe hockey or basketball or something like that, volleyball, who knows. So it takes a lot of space to host a big concert or something like that. So don't be frightened by the fact that's a huge number. Volume numbers are often big because what this means is if you had a bunch of cubes or a bunch of boxes that were 1 by 1 by 1, how many of them could you fit in the arena? It says you could fit 32 million of those boxes. That makes sense. Those boxes aren't very big, and that's a big, big arena. Now let's try an example with a cone. Okay, so volume of a cone, and pause the video, draw it if you want to. Try this on your own first, okay? I think you can probably get it. Okay, we said the volume was the 1/3 pi r squared times the height. So let's see. 1/3 times pi. Do you know what the radius is? It is not 30 or 25. It's 15. 30 is the diameter. So we're going to go with 15 squared times the height. Yep, makes a right angle. So we're perfectly good. So 25 there. And the only thing I want to point out to you here, you see how this cone is not perfectly symmetrical? It's sort of slanted. Does that change the math at all? Does that change our calculation? It doesn't. Remember we talked about Cavaliere's Principle a little bit ago. If you have a shape that's a little bit skewed, that's no problem. Cavaliere's Principle tells us that our understandings will still apply. So let's type these in the calculator now. So I get 15 squared times 25 divided by 3, and I get 1,875 pi cubic feet. Now let's finish today's lesson with a quick conversation about volume of spheres and how to find them, how big a sphere is, okay? I'm going to give you the formula on this. It is 4/3 pi r cubed. If you want to see an in-depth explanation of why that is, if you go to the Solids of Revolution video on my calculus feed, you can see a really, really in-depth reason for where that formula comes from and why it works. But for today, we're not going to use calculus to prove this because we're only in geometry. We're just going to go for it, okay? So we have two spheres here. Spheres are kind of challenging for me to draw. I mean, I can see how you do it. You draw a circle and you draw a little oval inside and you make the backside of it dotted. I'm not going to worry too much about that. I'm not going to expect that you know how to sketch spheres. I am going to expect that you know how to find their volumes, though. So let's practice. Okay, so for this sphere, we have 4/3 pi radius. Okay, that's 6. So that'd be 6 cubed. Okay, and so what do I get when I do that? 6 cubed, and I'm going to multiply that by 4/3, and I get 288 cubic meters when I do that. So y'all, I hope you can see this is straightforward. This is one of the easier ones. There's only one variable. That makes it probably the easiest shape to work on. Same thing over here. Y'all pause the video and try this one. It's 4/3. I'm going to pause just for a second so you can stop the video and try it on your own. Okay, for this one, we're going to have pi. Have you identified the radius yet? It is not 8. 8 is the diameter, so we need half of that for the radius, so 4 cubed. So calculator time, don't forget to divide by 3. That's a common mistake people make. And so I'm going to probably not use a decimal on this one. It doesn't divide out evenly. So 4 to the 4th, or 4 cubed times 4 is 256. It's over 3. And then we still have a little pi right there, okay? So, and then I forgot my meters cubed, so let me put that on there. So that's how we find the volume of a sphere. Now, sometimes the questions are not as straightforward. I started out with 2 really easy examples, so let's look at one that's a little bit more challenging and see what an application of this is. Okay, so given that the Earth's equator is 24,902 miles, we need to approximate the volume of the Earth. Okay, so what I like to do on a question like this is I like to set up the information that I know. I know that I need to find volume, and I know that that is 4/3 pi r cubed. Do I know the radius? No, I don't. Okay, they gave me the equator. And where does the equator go on the Earth? The equator goes all the way around in a circle. So I know that whole thing is 24,902 miles. I need to be able to connect that circle to a concept. And for me, what I see is I see the circumference of the Earth all the way around, wrapping around its longest point. That is what is 24,902 miles. So we need to remember back to what we learned previously. What did we learn? We learned that circumference is 2 times pi times the radius. So that is 2 times pi times the radius is 24,902. If I wanted to know what r was, I would need to divide by 2 pi. Now, I'm going to leave this in as exact a form as I can. So I'm going to type in 24,902. I know you can probably do this in your head, but I'm not going to. Divided by 2, and so I'm canceling out the whole numbers here, and I get 12,451. 12,451. The pi is still there. And I'm going to leave the pi there right now because every time I round in the question, if I type it in, it'll round the answer. Every time I round, I lose precision. So I'm going to retain that right now. So about a minute and a half ago, I said, wait a minute, do I know the radius? I don't. Shoot. I've now enacted a process that allowed me to find the radius. Now that I know the radius, I can go back and find the volume. So 4/3 pi for r, I'm going to write that whole big thing. 12,541 divided by pi cubed. So now I have a setup for volume. And now I'm going to go to the calculator. They said approximate, and it's a contextual question. So I'm actually now going to type pi in the calculator. I'm not leaving this answer in terms of pi, because if you say something like, well, the volume of the Earth is 300 million pi cubic feet, it's very difficult to understand what that means. So we want this rounded. We're probably going to go to the nearest whole on this one, okay? So let's go for it. What I like to do is I start over here in the calculator. So I'm going to type in parentheses 12,541 divided by pi, and I'm going to cube that and just see what that is. Okay, and I get a big decimal. And then I'm going to multiply that by pi and 4 and divide it by 3, and I get this crazy looking answer, 2.66398,393 times 10 to the 11th. Okay, now we have not spent a ton of time dealing with this type of deal over here. Okay, this is scientific notation, and what it says is we need to move our decimal 11 places to the right to make this number bigger. So here I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, that gets kind of hard to see, y'all. So I'm going to redo that down here where I have a little more space, and it's a little bit easier to explain it. So 2.66398,393. Okay, 11 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's where the decimal point should go. The calculator doesn't have enough digits to write all that out. That's why they use this scientific notation. So in these, I need placeholders. 0 works as a marvelous placeholder. I'm going to go in and put commas so I can actually tell how big this number is. So every 3 digits, put in a comma. So I have, there's my 100,000s. There's my millions, there's my billions. So I think a little bit of rounding is probably in order in a question like this. I think I'm going to round it to the nearest million. So that'd be 266,398,000,000. And what are the units? Cubic miles. Okay, that is the approximate volume of the Earth. And that's a big number, but y'all, the Earth is a big place, right? It's pretty big. It's big enough that it was able to capture the moon and hang on to it. And it keeps you from jumping very high. So the Earth is a mighty big place. Okay, so that's an example of an application we could use. Maybe you can find some other applications that are more relevant to your own situation or your own life. That's going to be it for today's volume video, okay? We've talked about how to find the volumes of prisms, cylinders, cones, pyramids, and spheres. I hope you enjoyed the video, and we'll see you next time.